Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 4.1.4, which is Factoring Completely. And the basic premise of this chapter is recognizing when a quadratic can be factored multiple times. Now, up until this point, we've factored each quadratic only once, but now, by the end of this chapter, you should be able to recognize when a quadratic can be factored more than once. And we'll see that happen in later examples. In this particular problem here, we'll see one of them run into that problem, but we will learn how to tackle that very soon. So in A, we're just going to go through the basics of factoring again. With A, what I'm going to do is I'm going to go ahead and create my diamond problem here. And I'm going to get a 36x squared up top and a negative 12x on bottom. And I'm looking for two numbers that multiply to positive 36 rather, and add up to negative 12. That's going to be negative 6x and negative 6x. And again, if you haven't gotten sick of it by now, here it comes. Here comes the area model. It's 9x squared and 4, negative 6x and negative 6x. Looks like I'm going to get 3x and 3x. And looks like I'm going to get a, not a plus, but a minus, minus 2, minus 2. And we end up with this 3x minus 2 times 3x minus 2. Some people might consolidate that into 3x minus 2 squared because this, once again, is a perfect square trinomial. In B, we have 81m squared minus 1. So if I wanted to, I could call them 81m squared plus 0m minus 1. In my diamond, it would be negative 81m squared up top with 0m on bottom, so it looks like negative 9, not x, but m, and 9m. So then in my area model here, we're going to get 81m squared with a negative 1 here. So what I'm looking at here is I'm looking at two numbers that do that. So I'm going to say it looks like negative 9m and 9m. So this thing is going to break apart into 9m and 9m with looks like a negative 1 up top and a positive 1 on bottom. So I got 9m plus 1 times 9m minus 1. Now again, perfect square trinomial. And then this is a difference of squares. Make sure you recognize the difference, right? In a difference of squares, the terms have the base and height have the same terms, but a different sign. In the perfect square trinomial, the base and height have the exact same sign. So make sure you keep that in mind. With C, we'll go and write that in order. So x squared minus 11x plus 28. And we will go ahead and area model this guy out. So it looks like 28x squared and negative 11x. So I'm looking at negative 7x and negative 4x. Into the area model we go. So x squared and 28, so negative 7x, and negative 4x, so x, negative 7, negative 4. And now I've got x minus 4 times x minus 7. And the last guy is going to be where things are a little bit different. So I'll go ahead and pull him up here. So 3n squared plus 9n plus 6. And now I've got 18n squared with a 9n on bottom. And I believe the two numbers that are going to do that are going to be 6n and 3n. And into the area model we go. So I'm going to say 3n squared with a 6 up top. 6n, 3n, looks like 3n and n. So this is going to be plus 3. And that's going to be plus 2. So it looks like I'm going to have n plus 2 times 3n plus 3. Now pay close attention to this term right here. Whoops, forgot to close off his bracket. Pay close attention to this term here because you're going to see something happen to him in the next problem here. They're going to review that problem in just a second. But for now, this is just a good warm-up. It's a good segue back into the factoring. We have the area model. We have the diamond problem. It all comes back. I'll be back with the next question. Give me a second. And in 4-35, it says, compare your factored expressions with the rest of the class. And in A, it says, is there more than one factored form of the 3n squared plus 9n plus 6, which is question D. It says, why or why not? Well, let's find out. Is there? Well, remember, in the past videos, I've told you the arrangement of those two diagonal terms doesn't matter. So let's find out if I rearranged them and put them in a different order, would I get a different answer? So this is 3n squared and 6. if I throw the 3n here and the 6n down here, now I'm going to go ahead and say go 3n here and then n right here. This will be, looks like plus 6, right? And I believe this is plus 1. Now, I believe this actually does work. And so how is it that I could actually end up with this situation where I have n plus 1 times 3n plus 6, and how could that possibly equal n plus 2 times 3n plus 3? And does it actually pan out? Well, let's find out. Let's see, I'm going to get 3n squared, 6n, 3n, and 6. These guys will combine out. 3n squared plus 9n plus 6. So it looks like this guy works. Now, does this guy actually work? I get 3n squared plus 3n if I multiply him, plus 6n, plus 6. Those are definitely equivalent statements, so 3n squared plus 9n plus 6. So they seem to equal, but what the heck's going on here? How is it that two different arrangements could actually happen? Well, that's exactly the reason. It's because there are multiple arrangements for this particular quadratic. Now, what I want you guys to do is I want you all to look at that expression, and I want you to see if it's different than the other ones. The other ones are this guy, and this guy. Is there something different about that? And you're supposed to be pondering that as you move into part B. And then in part C, it says, without factoring, predict which quadratic expressions have more than one factored form. Now, after having a discussion with your team members, what you're supposed to conclude is that this one will have more than one factored form, and so will this one. This guy here will not, and this guy here will not. These guys have only one form. But these two, they have multiple forms. So let's talk about what they have in common. Well, if you look at 12t squared minus 10t plus 2 versus something like 5p squared minus 23p plus 10. Well, notice the terms, right? 12, 10, and 2. This is 5, 23, and 10. These have a common divisor of 2. This one, there is no common divisor. So that means that there's only one arrangement of this, but there's multiple arrangements here, because if they're all getting multiplied by 2, there are a few different ways we can scale factor this quadratic up or down or rearrange the terms. So from here, we'll go and explore that idea in the next problem. Give me a second. And lo and behold, in 4-36, they unveil the curtain and they say, part C of problem 35, you should have noticed that 12t minus 10t plus 2 is divisible by 2. That means that each expression has a common factor of 2. Now, one thing I want all of you to keep in mind is this notion of factoring, and I'll even type this in for you all. Factoring is division. Factoring is division. Because we are essentially reversing the distributive property, right? And if the distributive property is multiplication, that means that factoring is division. So what we're going to do is we're actually going to go ahead and factor this 12t problem first. So 12t squared minus 10t plus 2. I'll go and switch colors back to white here. If it's divisible by 2, what I'm going to do is I'm going to factor out that 2 first. This 2 is going to come out. I'll even draw it lower. And then that's going to get multiplied by an entire thing. Well, the way I get the pieces that go inside this parentheses here is I am literally going to be dividing each term by 2, and those make up the 3 terms on the inside. So what I get is 6t squared minus 5t plus 1. And now I'm going to go ahead and area model this guy out right here. So what I have is I have 6t squared and negative 5t, which is going to be, looks like negative 3t and negative 2t. So in my area model, what I'm going to have is I'm going to have 6t squared with 1, negative 3t and negative 2t. So I'll go and throw out my 3t and my 2t here. Looks like minus 1, minus 1. And so what I have now is I have 3t minus 1 times 2t minus 1, but I can't forget this 2 that came along. This is what's known as my GCF. And that stands for GCF. That stands for greatest common factor. And we always want to pull that greatest common factor out for a couple of reasons. One, because a term is not considered completely factored until the pieces are broken down such that they can't be factored anymore. Having said that, factoring out a greatest common factor in the beginning is always advantageous, because what does it do? Well, it lowers the number value of each of my trinomial pieces. And generally speaking, when it comes to making an area or diamond, smaller numbers are going to be easier to work with, because generally speaking, smaller numbers are easier for us to conceptualize than bigger numbers. So I always recommend pull that GCF out first. You always want to be on the lookout for that GCF every single time. If you can pull the GCF out, you want to pull that out as soon as possible. That way you can factor something that has smaller values. Let's go ahead and take a look at B here. We have 10x squared plus 25x minus 15. We're going to factor that thing completely. So again, what do they all have in common? They all have a 5 in common. I'll pull that 5 out of there. What happens when I do that? That means that each of these terms is being divided by 5. I get 2x squared plus 5x minus 3. And that is going to be a little bit easier to deal with. So negative 6x squared, 5x. I'm thinking if that's going to happen, I'm thinking let's look at 6x and negative 1x as my two pieces. Into the area model we go. 2x squared and negative 3. So I'm going to throw in a 6x and a 1x here. I'm thinking 2x, 3, and 1, where this is going to be, oops, that should be negative 1, so negative, positive. So I'm thinking 2x minus 1 times x plus 3, but don't forget, please don't forget, that 5. And you're going to forget that 5. Don't forget that 5 like I almost forgot. So there goes your term, your quadratic term completely factored. I'll be right back with the next example. And what a wonderful way to end up this section here with a little bit of drilling. So we're going to factor these expressions completely. Again, please, I can't emphasize it enough, please make sure you pull that GCF out first before trying to factor this thing. Otherwise, you end up with multiple versions and it gets a little confusing. So we don't want to end up there. Easier is always better. And so factor out that GCF, get smaller numbers. It'll make the factors so much more clean for you. It looks like I'm going to throw down a 4x and a negative 1x here. Into the area model we go. X squared negative 4. And so I'm going to throw down a 4x here and a negative 1x down here. So xx, 4, negative 1. Hopefully by now you're getting a little bit faster at the area model. And I'll throw down the 5 right there. And there we go. Look at B. It looks like 3x cubed minus 6x squared minus 45x. Looks like I can factor a 3x out of there. That's my greatest common factor right there. So if I do that, looks like I'm dividing everything by 3x. And again, don't feel afraid to draw this literal division going on here. And so it looks like I'm going to get x squared minus 2x minus 15. And so we'll go and throw that down to the area model. So that's going to be negative 15x squared, negative 2x, negative 5x and 3x. And here we go. Into the area model, x squared, negative 15. Again, I'm going to disregard this 3x for now until I need them back again. Negative 5x and 3x, so xx, negative 5 and positive 3. Again, I'm just finding the dimensions of the rectangle, right? And so I'm going to go x plus 3 times x minus 5. Don't forget that 3x that exists right there. And then C here, again, factor out that 2. I get x squared minus 25. Now from here, area model. So it's going to be negative 25x squared, 0x. So negative 5x, 5x. Into the area model we go. So I get, looks like x squared negative 25, negative 5x, 5x, x minus 5, x plus 5. So 2 parentheses x minus 5 times x plus 5. Again, notice how I'm not forgetting to bring down that GCF. You will forget to do that. Please don't. You will lose points if you forget to bring down that GCF. Okay, with D, looks like we're going to factor out a y. Look and notice how I see that so quickly, right? And it's not partly it's because of experience, but you can see it too. Look for what they have in common. And so you have x squared minus 3x minus 10. And so again, into the area model. Negative 10x squared, negative 3x. I'm looking at, it looks like negative 5x and 2x. X squared, negative 10. So it looks like I'm going to negative 5x and 2x here. X, negative 5, and 2. So y parentheses x minus 5. And again, notice I did not forget the GCF that we pulled out. Please don't forget. Please don't forget. And that will pretty much wrap up this lesson here with factoring completely. Again, the biggest takeaway from this lesson is to make sure you factor out those GCFs first if you ever see them. That's the first thing you should look for. And an expression is not considered completely factored until it can't be broken down anymore. If you notice, in every example, we couldn't factor it anymore. And so that's what you want to look for in each of these quadratics. Feel free to leave any comments or questions in the comment area, and I will see you in the next episode.